How you doing, Mr. Yang?
Pretty good. Pretty good. Hope you guys got a chance to enjoy the outdoors yesterday. It was nice. Okay. So textbook request is closed in terms of I sent the final list just now to Ms. Duke, and it should be ready for pickup tomorrow through Friday. And again, physical textbook is not required. It is we all have access to the digital one, and ultimately, for any assignment, I'm going to be pulling from the textbook, and I'll make a separate PDF file within each day, so you don't need a textbook. But some students just want to have one, and so that can be. So when you follow the link I sent this weekend, you'll see the instructions in terms of what days to go based off of your last name and what information to provide the helpers, your name and the textbook you want. Okay. But I'll confirm. I think she meant for it to be starting tomorrow through Friday, but based off her wording, Ms. Duke's wording, I don't know if she meant this week or next week. So let me confirm that, and I'll let you guys. I'll give you guys a text remind this afternoon. Today is also when your classwork for Unit 1 limits is due. So classwork are just the problems that we did in class, the notes that you took in class. Some of it we didn't finish, so we're just the whole purpose of this is for me to have evidence from you that you are participating and that you are attempting the problems, yeah, and this is going to go in as a formative grade based off of how much you've completed. And late turn-ins are okay, so if you don't have it ready today, you can turn in to me sometime this week. So it will go in, I think, put it in as a 100-point grade, but ultimately it is just a formative grade, meaning that if you don't do any of your homework, it won't count against you, right? It is just for me to see how you're doing in class in terms of, but it's not going to affect your grade, right? So any questions about this process? Oh, some students were asking, can they use OneNote? That's fine, you can do OneNote, but I don't know OneNote very well, so see if you can play around in terms of, can you get a link to it? Can you put that link into the submission? And I'll see if I can access it. If I have a problem accessing it, then maybe I'll ask you to do screenshots of it, put it into a Word document, or take a picture. But yeah, so we'll kind of play around to see, try still figuring out. But I'll let you guys know if after you turn in your classwork, I can't see it, or if I'm having trouble accessing it, I may ask you to resubmit it. But yeah, no late penalty because it doesn't count for a true grade, just a way for me to monitor our progress. All right, any questions? Classwork? I'm going to have, so you've been printing out your notes from my website, and every time you print out your notes, you see the date that we are doing those notes, right? So today, September the 8th, Tuesday, that's where you got the notes for 2.1. And I'm going to start adding a homework section below it. So I don't want to add additional burden to your to maybe all the other coursework they have to do. But I do find that it is important for us to get additional practice outside of class. So I'm going to try to limit to 5 to 10 questions. If you don't get to all of it, or you feel comfortable enough where you don't have to do all of it, that's fine. So, but I really feel that getting in the practice on our own, besides, it's a different process between watching someone do the problem and actually doing the problem yourself. And when we do the problem ourselves, that is when we begin to process things a little bit better in terms of, wait, I thought this was this, how come it's not working out, right? We're able to see what we really know when we try the problems on our own. And also, if you are stuck, right, those problems, those concepts will stick a little bit stronger if we're working through that process on our own. But again, these are daily homework that is going to go in as a formative grade, meaning that if you don't do all of it, or if we just do some of it, or we don't do any of it, right, I'll put in a grade, but it's not going to count against you, right? So I don't want you to stress about these either if you don't get to all of it, right? But I'm going to try to limit it to between 5 and 10 questions. When you click on it, you'll see a blank copy. At least I'm going to try. I'm trying to have blank copies that we can, if you want to print it out, or you can do it on a separate sheet. But I'm also going to attach a key to it so that you can kind of check your work along the way. Okay. But formative grade. Okay. And then I'm going to collect these at the end of our after our next assessment. Okay. Starting tomorrow, we are going to be on an asynchronous Wednesday, meaning that there's no live sessions on Wednesdays. Okay. And if there is anything that teachers do on Wednesdays, they're all going to be optional. Okay, so none of it is required. So what I'm going to do is I'm not going to assign any homework on Wednesdays. All I'm going to do is I'm going to offer a morning help session, extended help session, 7:30 to 8:30, and I'm going to treat it like a catch-up day, in terms of not catch-up day. I'm going to just go over the previous night's homework. So tonight you have homework from 2.1. Tomorrow during this help session, I'll be going over those homework problems. And you don't have to attend. You don't have to attend if you don't want to, because we're not covering any new material. And if you don't want to attend but still want to access it, I will record it, so you can definitely look at it at a time that is convenient for you. But it's going to be in the Calculus Help Session channel. It's not required. I'm not going to assign any additional work. I'm just going through the previous assignment. So tomorrow I'll go over today's assignment. Any questions about Wednesdays? So it's a day for students to kind of catch their breath, for teachers to do a little bit of catch-up work, for teachers to maybe reach out to the students who need some additional support. Scheduling makeup test is also good for Wednesdays. So yeah, it's a little bit of a catch-up breather day before we finish the rest of the week. Outside of Wednesdays, I will have daily help sessions, a little bit shorter, 7:45 to 8:15, just going over the homework from previous nights. Again, I'm going to start recording these as well, because I just don't have time to go over homework in class. So I'm going to do it outside of class. And if you have questions, maybe you can attend it, or you can watch the video. And if none of this helps, then you can reach out to me, and we can go from there. Okay, so I'll make sure that you guys have the resources that you need for this course. Okay, no questions? And again, all these will be in the Calculus Help Session channel. I'll record all my sessions from here on out. Okay, so today we're starting with the topic of derivatives, but today is more of a kind of a conceptual day. We're going to see the connection between slope and derivatives and how we're able to kind of take a slope formula that is very restrictive, and we're able to now make it more robust using the concept of limits, and can adapt to more situations. And when we talk about derivatives, we're going to see how this is going to be kind of like the building block, the foundation for the rest of this semester, and in a sense, the rest of our school year. So here's our goal. Our goal is to find the formula to calculate the slope of all tangent lines to a curve. Oh, and by the way, if you have any questions at all, feel free to jump in and ask, because I'm doing the best I can to explain, but maybe some things you want me to repeat or you want me to clarify. Yeah, just jump in or let me know through in the meeting chat. So here's our goal. Our goal is to find a formula to calculate the slope of all tangent lines to a curve. So here's the distinction between a line and a curve in terms of slope. If I ask you for the slope, if I give you two ordered pairs and you find that slope is going to be the same no matter where you are on this line, right? But if I ask you for a slope of a curve, then your question is going to be, well, depends, or where, right? Are we talking about this point or this point or this point? Because every point on this curve is going to have a changing slope value, right? Depending on where you are on this curve. So this is a negative slope, that's negative slope, that's a positive slope, even steeper positive slope. So if I ask you for a slope of a curve, you're not going to be able to give me a number, but maybe there's a formula that will describe the ever-changing slope on the curve. Okay, so that's what we're after. We're going to start with the slope formula, and we're going to adapt it in a way where it will handle a curve instead of just a line. Okay. So let's say you know how to find slope. Let's say I gave you two ordered pairs, and that ordered pair was 1, 1 and 2, 2. Right, you'll take the slope formula, and you'll start putting it into the formula here. So the slope is just rise over run, change in y over change in x. So you would do 2 minus 1 over 2 minus 1, which is a slope of 1, right? Simple enough. So doesn't change, right? Slope is 1 here, slope is 1 here. It's everywhere on this line, the slope is 1. So the challenge comes if I ask you, what is the slope of this point? And if I give you that, even if I give you this point as 1, 1, this formula is not quite sufficient, right, to find the slope of the point on the curve. I see it here, but I'm not able. I need a second point, right? I need a second point if I want to use the slope formula. So what can we do then? Maybe we can start with the slope formula and we can adapt it in a way where we can achieve the slope that we're looking for, requiring only using one point. So this is what we're going to do. I'm redrawing the curve every time here just to help us kind of track our progress. So let's say the curve is f of x. Okay, I'll call it f of x here. And we need a second point. So let's just go ahead and find a second point on the curve. And you can tell that if I were to find the slope between these 2 points, it is way off, right? It is not close to what this target slope I'm trying to seek. So this is not a very good approximation. So maybe this is a slope of 2. But let's say, just for visual purposes, let's say the slope that we're targeting is 1/2. Okay, let's say that slope is 1/2, but our approximation with this point and this point is slope is 2. Okay, so we're in the ballpark, but we're not very accurate. So the question is there a way that maybe we can increase our accuracy of that second point so that our slope can be a little bit better approximation of this slope? Well, what if we bring Q a little closer towards P? So what if I were to choose a point that's a little closer than what I started with? And if you look, this secant line, so secant line is just a line that goes through 2 points. This secant line where I have the slope is a little bit better than what I had before, right? Still not great, but it's better. So maybe this is a slope of 1.5, but then I'm still seeking a slope of 1/2, but I'm not quite getting there yet. Well, if we can take the idea of bringing the point Q closer, then what if we just keep bringing Q even closer? Right, so if I bring it right next to it, maybe the slope ends up being 1 or ends up being 0.75, but it's still a little bit off from the slope that I'm targeting. What if we just keep bringing Q closer and closer and closer and closer? What if we bring Q into point P so close where Q disappears into P or falls into point P? So this is where limit is going to come into play. We're going to take 2 points, just like what we need with the slope, but we're going to drag that second point into the first one. And the way we're going to do that is we're going to decrease the distance between those 2 points. And the way we're going to do that is we're going to take limit as h approaches 0. So we're going to start off with some value of h, and we're going to keep decreasing it until there's no more distance between those 2 points. And now, if we can get Q to disappear into P, then we can just rely on 1 point to find the slope. Okay, we start with the slope formula. We adapt. We make it go through a limit process. And what started with 2 points is now merged into 1 point, and we can find the slope now with just 1 point. Okay, let me give a more concrete example because this is what we're after. We're going to be talking about this is our adapted slope formula that requires only 1 point because we're able to merge the concept of slope and limit together into one process. So we're working with this formula, but I want to talk about where this is coming from. I want to give a little bit of backstory in terms of, why this is related to slope. Okay, let's say we had point P and point Q again, but now I'm going to give it a little bit more information about these 2 points. Again, let's call this curve f of x. And again, we're going to start with 2 points some distance away from each other. Okay. This is, I'm not going to be using numbers. I'm using variables here because we want to have a much more, we don't want just a static situation where it only applies for a specific problem. We want to make it more general so that it can apply for any point that we want to use. Okay, so that's why we're using all these variables here. We're coming up with a formula that can be adapted to any order pair. So let's say we have some order pair that is x distance away from the origin and x f of x. If I plug x into the function, I get f of x. So that is the order pair that represents point P. Now we started with point Q being some distance away from point P, which means that wherever this X value is, I need to go a little further before I can find point Q. And what I mean by a little further is I need to have some distance away, and that's what H is doing. H is going to be some horizontal distance away from our starting point. So maybe this is an X value of 1, and this is 4, then it'll be 1 plus 4, which is 5. Or if this is 2 and this is 7, then 2 plus 7 is equal to 9. Right? So we're creating a distance between those 2 points, and we're calling it H. So if X plus H ends up being the X value location of my Q, then if I plug X plus H into the function, then what I'm going to get in return is a Y value that represents this graph or this point. So my ordered pair for this Q, which is some distance away from point P, is represented by X plus H being the X value, and then X plus H into the function will give me F of X plus H. So it looks messy, right? It's a lot messier than using 1, 1 and 2, 2, but we have the flexibility now to adapt to any order pair that we want to use. So let's still find the slope that we did before, but now just using these notations. So I'm going to call this x1, y1, and I'll call this x2, y2. Just like before, we're going to find the slope. So y2 minus y1 over x2 minus x1. So let's see what that looks like. Y2 minus y1 all over x2 minus x1. Okay, any questions so far? Okay, let's see if we can do any sort of a cleanup with this expression. Not much we can do with the numerator. These aren't like terms, but if you look at the denominator, looks like we can do a little bit of cleaning up, right? The x's can cancel out. So look at what we have here. Even though this looks strange, this is really slope formula in function notation. Okay. I know it looks very cryptic. It looks just like a random set of expression here, but I want to ask, does this make sense? Do you guys see the connection between something that we know with this new adaptation that we just made? Okay. So now what we're going to do is we're going to take this slope formula, and now we have this h, which represents the distance between P and Q. But we have h being a variable because we want to move it, right? We want to decrease that distance between the 2 points. So what we're now going to do is we're going to attach this limit notation in front of our slope formula. So we're going to decrease the distance of h, decrease the value of h. If I decrease the value of h, then the distance between P and Q is going to grow smaller and smaller and smaller. And the idea is that we can, if h approaches 0, then we can make the distance between P and Q non-existent, where we can just eventually move Q into point P, and that will help us achieve the exact slope of a point on the curve. Okay, so we're taking our order pairs from our slope and we're merging those 2 points together. Okay, let's talk about notations here. You see this F with this apostrophe there. We call this prime. So F prime of X, that's how we say it, F prime of X. This is the notation for a derivative function. And a derivative is just the slope or steepness of a curve at a single point. So to put it in other words here, derivative is just a fancy word for slope. Okay. Derivative is just a fancy word for slope. As we get deeper and deeper into messier and messier notations, I don't want us to lose the big picture, right? If you can visualize the steepness of a curve, that's really all derivative is doing. As messy as the formulas can get, it's just trying to give us a way to find the slope of a point on the curve. So derivative is a slope finding formula for a curved function where the slope is ever changing. Okay. There's also this alternate definition, which I'll get to maybe another day, maybe Thursday. But today I just want to focus on this general limit definition of a derivative. And I just want us to be able to see that connection between slope formula, but now it's in function notation. And we do it so that we have the flexibility of moving that second point towards that first point. Okay, any questions so far? Okay, all right, let's do an example of a problem on the back here. Okay, example 1, find the general derivative of f of x equals x squared. So general derivative, we're going to find the slope formula. Another word for that. So this is what x squared looks like. It's just a parabola. So we're going to create a formula that will describe the steepness of every point on this curve. Right? That's our goal. And the way we're going to get there is using this limit definition of a derivative. Now, this is the formula that we're going to be using, but this is the specific function, the specific curve that we're trying to develop the formula for, which means that we have to get this updated with this particular problem that we're trying to solve. Now, we know what f of x is, right? f of x is x squared. I think the issue that students have is understanding how to get this f of x plus h into this x squared. And this is where some of us struggle. We usually do this in chapter P to kind of get used to the notation, but now we lost chapter P, so I'm just inserting what we need within the lesson. So So over the years, I've been trying to figure out, what is the best way to get us to, so that we don't make a mistake or know what to do when we plug that x plus h into that x squared. So let me talk about the process. I'm going to put this on the side here, kind of a side note. if I'm trying to get from f of x to x into f of x plus h, okay, this is what we can do. If I'm trying to get from here to here, I think if we can do this middle process. Now, you don't have to do this middle process if you're comfortable with getting it into f of x plus h. You don't do this, but I find that this is helpful to give structure for students who have maybe need more help kind of seeing where this goes. What you can do as a middle step is you see these x's here. Remove those x's and put parentheses where those x's used to be. Okay. Does this step make sense from here to here? All we're doing is every x that we see, we're just going to put parentheses around it and we're going to remove the x. Okay. Are we good so far here?
Yes.
Okay, thank you. Yeah, thanks for confirmation. I just want to make sure that I'm not jumping into something that's moving too fast or something not making sense. Okay, so now once you have this, then you have the structure that you need to build that f of x plus h. So everywhere you see a parentheses, just put an x plus h inside. There we go. And having this middle step is helpful. Otherwise, students struggle with knowing where to put that h. So our f of x plus h is just going to be x plus h squared. And our f of x is just x squared. Okay. So let me just go off on a tangent a little bit more here. Let me do a more extensive function and see if this process makes sense. So let's say I gave you a function that's a lot more complex. We're not going to do this one for this problem, but just to help you connect it more. Let's say it was 2x cubed minus 4x squared plus 6x minus 9. And I asked you to find f of x plus h. I think if we can do this middle step, it'll give us the structure that we need to get this f of x plus h. So just like before, with this problem, every x you see, remove it and put a parentheses in place of the x. Okay, can we go from here to here? It's more intensive than the previous one, but let me know, does this make sense here? Okay.
Yeah.
Good. So now this is right. If you can do this, then this should be easier because literally you're just going to put an x plus h in the space between the parentheses. So even the most complex expression, you won't make a mistake because you have kind of boundaries to help you know where to put that x plus h. Okay, any questions with the process? So if you don't do this, this is what I see from students who have trouble getting that x plus h. What I see sometimes is they don't know where to put that h, so they do this. And they just attach the h to the end because they know the h has to go somewhere, so they put it there. So this is not how we interpret f of x plus h. Yeah, so this is a common mistake, but if we can do this, we can kind of see better how to fill in that x plus h into our expression. Okay, let's go back to our problem here. Okay, we have everything that we need. So f of x plus h will be replaced with x plus h squared. F of x is just the original function. We can clean this up, right? We can FOIL this, expand this. Well, actually, I'm sorry. First thing we do, right? The first thing we do when we see a limit problem, we always try to evaluate, right? So 0, let's replace 0 in for h, just like what we did first unit. 0 in for h, we get x plus 0 squared, which is x squared. X squared minus x squared is 0. Denominator, replace h with 0, we also get 0. So if we get 0 over 0, we know there's a hole. And if there's a hole, we know we want to try to cancel things out. We can expand that x plus h. Okay, we're going to keep foiling out. Cleanup process. X squared cancels out. So what do you guys notice? Is there anything we can do to clean up and get rid of the hole? What do you guys see? What can we do?
Factor out h.
Yeah, factor an h out. So with these problems, you're always going to be able to factor an h out. If you can't factor an h out, something didn't quite go right. That means every term is going to have an h in it. So if you see a term in the numerator after everything is cleaned up that's missing an h, we got to go back, right? Something got lost along the way, because we're always going to be able to find the limit. We're always going to get the h's to cancel out. So now, any remaining h's, because we know that the hole has been removed, so we're in the clear now. Every h can now be replaced with 0, and we're not going to run into a 0 over 0 anymore. So 0 plugs in for h. 2x plus 0 is just 2x. So f prime is equal to 2x. So what we achieved here, we achieved a slope formula for this curve of x squared. All right. I want to step to the side here. I want to just have us do a visual exercise here. My graph is not accurate at all, but let's call this x squared. And let's say I want us to just look at 3 points here. So if I asked you, okay, so I'm not looking for exact value, I just want you to make your best approximation from a visual standpoint. If I asked you, what is the slope of the tangent to this point 0, what would your best guess be? What does that look like to you?
A slope of 0.
Slope 0, right? It looks like slope 0, right? We'll confirm in a second, but it looks like slope 0. Here at -1, what does that slope look like to you?
Slope of -1.
Okay. Slope of -1, maybe -2, somewhere in that range, right? Okay, now I'm not asking for exact value, but we know that, okay, it doesn't look that steep, but it's definitely negative. So our best guess, maybe -1, -2, okay. What about here? What's your best guess?
Two or a 3.
Say it again?
A 2 or a 3.
Okay, maybe 2 or 3. Okay, I would say definitely steeper than what we had before, but maybe even steeper than that. Okay, but we know it's positive. We know it's steeper than the negative version of it, so we'll say 3 for now. Okay. But we can see visually how we would interpret it, right? Even if everything is not accurate, we know how to read a negative slope within a zero slope and positive slope, at least to the best of our abilities, right? So now, let's see what this slope formula can give us about this graph that we were just estimating along the way. Okay, f prime equals 2x. This is my slope formula. If I give it any x value in return, it'll give me a number, and that number will correspond to the slope at any point on the curve that I'm looking at. So f prime of 0 means I want to find the slope of this curve at 0 before our guess was 0, and the actual slope is also 0. Okay, so looks like our guess was perfectly correct. F prime of -1 will tell us the exact slope that we were just doing a guesstimation on. So if I plug -1 in for x, I get 2 times -1, which is -2. So looks like our guess was, at least one of our guesses was correct. Okay. And over here at 3, we guessed that it was a positive slope, steeper than before, but positive slope. So we can use this formula to not only gain approximation, it's going to give us the exact steepness of that point on the curve. So f prime of 3 is going to be 2 times 3, and the actual slope is actually a little steeper. It's actually at 6. Okay, one final thing that I want to do before I let you guys go is I want us to see that distinction between function and derivative. You see how the function and derivative, they both describe the same graph, but they provide a slightly different information, even if we give it the same x value. So if I say f of 2, I get 4, but if I get f prime of, I'm sorry, 2 is not a good example. If I do f of 3, I get 3 squared, which is 9. If I do f prime of 3, I get 6. And the distinction is that the 9 tells us the physical location of the graph. The 6 tells us the steepness of the graph at that point. Okay? And this begins our process of understanding the distinction between a function and a derivative, and that they describe the same graph, but they give us different information about the graph. Okay, tomorrow I'm going to go over the homework, but it's just, it's just going to be a help session, not required. But you guys can try the homework, and I will see you guys on Thursday. Okay, thanks everyone. Have a great day.
Thank you.
Bye.
Have a nice day.
See you guys. Have a nice day.
Bye, Mr. Yang. Thank you.
Bye. Have a good day. See you Thursday.
Mr. Yang, I've got a question.
Sure.
I didn't exactly follow along the beginning. Where do you want us to insert our